Hello. Today we're going to continue the study of SGD, but at a much more theoretical level. Last time we talked about a lot of things that were pragmatically useful, especially in tuning hyperparameters and various forms of practical SGD. This is going to be more theoretical, so in some sense more challenging and interesting. And it's going to be based on stochastic differential equations. This is one of the scariest subjects in deep learning, stochastic differential equations. It sort of is taking calculus differential equations to a higher level of complexity. So my sympathies, this is going to be challenging. But we're going to warm up with something simpler, which is an ordinary differential equation called gradient flow. And this is pretty simple. And then we're going to try to get a formal understanding of stochastic differential equations in general, starting with Brownian motion. You've probably heard of Brownian motion. And then I'm going to talk about Langevin dynamics, which is another subject that has gotten some attention in deep learning. Langevin dynamics is about sampling from a Bayesian posterior on your model space. And then I'm going to apply stochastic differential equations to the understanding of stochastic gradient descent. And I promised in the last lecture to give a formal interpretation of the learning rate as temperature. And we can do that with the stochastic differential equation model of stochastic gradient descent. Okay, but let's start with the simplest thing that I want to talk about today. I understand this is a lot to cover. So we're going to start with something simpler and see how far we get. Gradient flow. So gradient flow is a deterministic differential equation. And I've written it down here in red. Phi here is the model parameters. So these are the parameters of some model. And I'm going to define a time derivative of the model parameters. So if you think of the model parameters as living as a point in a vector space, there's going to be a derivative, which is a gradient direction in that vector space. And we're going to take the gradient direction to simply be the gradient of the loss function in the model space. So we're going to be moving along the gradient of the loss function continuously and smoothly, and that is a differential equation. So we'll start with some phi zero, that's some initialization, and then this differential equation defines a continuous path through parameter space. So here's the differential equation. The derivative, the derivative of the parameter vector in this parameter space is minus the gradient at that parameter vector, the gradient of the loss function. And here I'm considering a total loss, or maybe an average over the population. I'm not sampling. This is the total loss, or the average loss over the population. Okay, so this is a differential equation. For small values of delta t, I can numerically integrate this differential equation by taking the change in the parameter space to be minus the gradient, that's the gradient direction, times the change in time. We'll take little steps in parameter space. This is simply the numerical integration of this differential equation. Now, there's a relationship between gradient flow and stochastic gradient descent. And so that's the first thing I want to talk about. So here's the differential equation. I've written it as the differential in parameter space. The differential change in parameter space is minus the gradient times the differential change in time. Now, this is the numerical approximation of that. So this is the numerical approximation of gradient flow. it's saying phi at t plus delta t is roughly equal to phi of t minus the gradient times delta t. So this is just how you would numerically integrate this equation. Okay, I want to look at this equation and compare it to stochastic gradient descent. Here's SGD, and I'm going to write, I'm going to consider the sum of the learning rates to be, I'm going to think of that as time. So here's the SGD update. We take the parameter and we subtract a learning rate times an estimate, a noisy estimate of the gradient. Now, these two equations look identical, except I've replaced the delta t by the learning rate. So I'm going to interpret the learning rate as delta t and say phi of t plus the learning rate, that should be eta t, is approximately phi of t minus eta t g hat. That's SGD. So what is going to happen is that as the learning rate goes to 0, as we take the learning rate to 0, SGD is going to converge to gradient flow, to continuous gradient flow. And that's the same as saying that as this numerical, it's similar to saying that as this step size goes to 0, our numerical integration will become accurate. But there are two issues here. One is that the step size, we can take the step size to 0, but this G is the true gradient, whereas in SGD, we're using an approximation of the gradient based on a mini batch, or maybe even just one sample point. So G hat is just something whose expectation is G. So we've got two issues in showing that as eta t goes to 0, SGD converges to gradient flow. So I'm just going to give a little proof of that. I apologize for proofs. What you really want to remember is this fact, that as eta t goes to 0, as the learning rate goes to 0, our SGD algorithm will approximate gradient flow. Will become arbitrarily accurate in approximating gradient flow. Will converge to gradient flow. So to prove this, I'm going to consider a sequence of model parameters defined by this equation, right? So this is the standard SGD equation. So I'm considering the sequence of model parameters computed by SGD. And this is the estimate, right? This is not the true gradient. This is SGD. So what I'm going to do is I'm going to take eta, I'm going to use the same eta at each point in time. I'm going to take eta to 0 and n to infinity simultaneously at the same time. Eta goes to 0 and n goes to infinity with this relationship. As eta goes to 0, n is going to infinity as t, I'm fixing a value t over eta. And what I'm going to show is that if I do capital N steps, where n is going to infinity, but eta is going to 0, such that the time, this interpretation of time is the same as eta goes to 0. So what we can do is we can divide this sequence, into blocks of size square root of n. So what's going to happen is in each one of these blocks, as n goes to infinity, this is going to converge on an exact step, which has time interval proportional to the square root of n. So this is going to, because we're doing an infinite, as n goes to infinity, this is an infinite number of updates. They're making an infinitesimal motion in model space, because to make a finite motion in model space, we need full n. So this is getting infinitely accurate, but infinitely small motion. So if each one of these blocks is getting infinitely accurate, but infinitely small motion, but if I sort of add them all together, right? If I add all these steps together, I'm making the whole transition to capital T. So I'm adding up a square root of n number of steps, each of which is becoming arbitrarily accurate. So I'm adding up an infinite number of infinitely small steps, each one of which is becoming arbitrarily accurate. So what you want to remember, I'm not sure if anyone followed that, but what you want to remember is that as eta goes to 0 under this limit, SGD will converge to stochastic gradient, to gradient flow, to the continuous version. Okay, that was the easy one. Gradient flow and the relationship between gradient flow and SGD as we take the learning rate to 0. Now things are going to get strange. As I said, stochastic differential equations is sort of the scariest thing in the theory of deep learning, but they're used in quite a few different areas. Right, in this lecture, I want to use them to understand SGD and to fulfill this promise of showing that the learning rate acts as a temperature parameter in SGD. So it's important for understanding SGD. It's also important, it's used in something called Langevin dynamics to develop an algorithm for sampling from a Bayesian posterior in the model space. And it's most interestingly, perhaps, fundamental to the modern diffusion models. You've probably heard of diffusion models, stable diffusion, DALI-3. Diffusion models are a big advance in image generation. And fundamental to diffusion models is a diffusion stochastic differential equation. And it turns out that the diffusion stochastic differential equation, which is the most interesting thing probably because diffusion models are so big, is the simplest version of a stochastic differential equation. So we're going to start with that. And a diffusion model, the stochastic differential equation underlying the diffusion model is also known as Brownian motion, which you've probably heard of. So we're simply going to talk about now Brownian motion. So I'm going to consider, first I'm going to consider a discrete time process. So we're going to have some value, Z0, Z1, Z2, Z3, and these are going to be vectors. Brownian motion, you know, when it was developed by Einstein, it was developed to model the motion of pollen grains in water. So in water, you have 3 dimensions of motion, and the pollen grains jiggle due to thermal motion. And so how do you model the jiggling of a pollen grain due to thermal motion when it's floating in water? So I'm going to, let's imagine taking pictures of that grain of pollen, that pollen grain at different times, discrete times, all separated by the same discrete interval. So I'll assume that we're starting at some position y, and then at each step, we're adding Gaussian noise isotropically distributed in that water. Okay, so we're adding some noise in the water. We're going to take the value at n. To get the value at n plus 1, we're going to take the value at n and add some variance times a random variable drawn from a Gaussian, a vector Gaussian, a random direction in 3-dimensional space. Now, if I take multiple steps, I'm adding together multiple Gaussians, and the sum of 2 Gaussian values is a Gaussian value. But the variance increases linearly, and the standard deviation increases like the square root of n. You should remember that from statistics, that if I add 2 Gaussian variables or I add a bunch of variables, the standard deviation goes as the square root of n if they all have the same variance. So that means we can sample Zn directly, right? I can sample Zn by starting at y and adding an amount of noise that grows with the square root of n. So even though I've defined this discretely, I can jump over steps and just increase the standard deviation by the square root of n. And I get a sample of where the pollen, the probability distribution of the pollen after n steps, and I can do that directly. And that fact is actually very important in diffusion models. The diffusion model is a model based on Brownian motion in very high dimension, the dimension of an image. And it's important that you can sample many steps of diffusion directly by jumping ahead and just adding more noise. Okay. So now we're going to consider a discrete time process where I think of this as a function of time, and I'm going to sample at 0 and delta t, 2 delta t, 3 delta t, and so because I can jump ahead, right? Because I can sample from this directly by taking the square root of delta t, the square root of the number of steps. I can sample from z plus delta t using this equation. If I'm adding, or I'm defining this to be the amount of noise I add in one step. I'm going to draw epsilon from this normal and then multiply by sigma and then take this single step. Now, the fact that I can step ahead means if I take z of t plus n times delta t, I can just put the square root of n into this formula. And now what we can do is we can take the limit of this numerical simulation as delta t goes to 0. How does this work? So because I can skip ahead, this n times delta t, I want to think of as t. N times delta t is t, because I've started at 0 and I've added n delta t, so this is t. So I can directly sample z of t by y plus this variance times the square root of t, right? This is the square root of t. And it turns out that this equation holds for any continuous t and delta t. In the limit, as delta t goes to 0, we get a well-defined probability distribution over where that particle of pollen is over time. That particle's position as a function of time is some function of time, but it's got, for any finite interval, it's got an amount of noise proportional to the square root of the delta t of that interval. So Brownian motion is defining a probability distribution over a function of t that satisfies this equation, that the value at t plus delta t is the value at t plus an amount of noise that goes as the square root of delta t. So for Brownian motion, we get this property. We're now talking about a continuous time function of t, where that pollen grain is at any moment in time. It's continuous time at any moment in time. It's random, and it satisfies this equation. So there exists this distribution over position and time that satisfies this equation. This is a way of sampling the next a step that's delta t further along. Okay, that's diffusion models. In a diffusion model, this z is an image. An image is just a vector in a very high dimensional space with one vector value for each pixel, or one vector value for each color channel of each pixel. And we're talking about an image, and we're talking about adding noise to the pixels of an image. We're adding noise to each dimension. That's what this does. So This is describing a diffusion model as a stochastic differential equation. And that makes certain mathematics go through. If you work in the continuous version, you can actually prove things that are hard to prove in discrete models. Okay, so that's the first application of stochastic differential equations, is diffusion models. Now, the second application I want to talk about is something called Langevin dynamics. And Langevin dynamics is about sampling from a Bayesian posterior on model parameters. So again, I want to think about model parameters, and I want to define a posterior distribution, the probability of the model parameters given the training data. And I'm going to assume a prior probability on the model parameters. We'll talk about Gaussian prior probabilities later, but we'll assume some prior density on the model parameters. And we're going to define a posterior density, which is the probability of the density of the model parameters given training data, is the probability of the model parameters and the training data, which you can write this way. I'm just writing down Bayes' rule, divided by the probability of the training data. Oh, okay, so the probability of the model and the training data is the probability of the model times the probability. Okay, I'm going to take the training data to be XY pairs. So this is like an image, and this is like a label of the image in ImageNet. And the probability of the training data given phi is the probability of the images, which is not determined by the model. The probability of the images is just the probability of the images, times the probability of the labels y given the images. And we'll assume independence, so this is just the product of this y1 given x1, and so on. So this is the probability of the model times the probability of the training data given the model. Probability of the model times the probability of the training data given the model, divided by the probability of the training data given the model. The probability of the training data generally. So this is the probability of, the probability independent of the model of the training data given the model. So the probability of x cancels, and this is the prior probability over the model times the probability of y given the model divided by the probability of y given the data. And that means that the probability of the model, this doesn't depend on the model, right? So the probability of the model given the training data is proportional to the numerator. This is kind of a long story, but it's a standard story in Bayesian inference. So I'm applying Bayes' law. By applying Bayes' law, I get this equation. And then the probability of the model given the training data is proportional to just the numerator. Okay. There's a lot of equations on this slide. I'm going to try to cover it at a high level. What we can do is we can define the loss function. We can define a loss function, which is basically this is cross entropy loss, right? This is a sum. This is the average over the training data of negative log model probability of y given x. That's the standard cross entropy loss for image labeling, image classification, or for any, probability of y given x problem, labeling problem. And here I've incorporated a prior probability, and you can incorporate that into the loss function. You can define the loss function to involve a prior probability, and that's called regularization. But the bottom line is that the posterior distribution on the model given the training data is proportional to 1 over z times an exponential in the loss of the model. okay, where this grows with this amount of, that n is the size of the training data. Okay, so what does this have to do with stochastic differential equations? Stochastic differential equations are going to give us a way of running stochastic gradient descent. And we're going to get a theorem that stochastic gradient descent run in a certain way with a certain level of noise has a stationary distribution which corresponds to the Bayesian posterior. So this is mainly of theoretical interest, but Langevin dynamics has had some attention in deep learning. And basically what Langevin dynamics does is it adds Gaussian noise to the update in the model parameters during SGD. And this Gaussian noise is added independent of, or in addition to, the noise that's coming from sampling data, right? When you sample data, the gradient is only an approximation of the gradient. So there's noise coming from the sampling process. And in Langevin dynamics, you add Gaussian noise on top of that. So my equations here analyze Langevin dynamics in terms of gradient flow. This is the gradient flow equation. So this is just a review of gradient flow. So what we're going to do now is change the SGD algorithm such that the noise due to the sampling is going to go to 0, because there was this theorem that as the learning rate goes to 0, the noise due to sampling gets washed out, and you converge to gradient flow. But instead of converging to gradient flow, we're going to converge to a stochastic differential equation, because we're going to add in Gaussian noise that will not be removed. Okay. So what we're going to do is we're going to add Gaussian noise to gradient flow. So I'm assuming the learning rate is small enough that we don't have to worry about the difference between G and G hat. This is just going to be G, right? So I'm going to add Gaussian noise to gradient flow. Okay, is that adding Gaussian noise to gradient flow, assuming that the gradient estimates are exactly correct. And we're going to take delta t to 0 in such a way that we're doing it like the way we did it in Brownian motion. So remember, in Brownian motion, you had this way of jumping over delta t steps and sampling. Given phi of t, we can sample from phi of t plus delta t by adding an amount of noise that grows as the square root of delta t. Okay, but so we have this version of gradient descent. It's really a version of gradient flow, but with Brownian motion-like noise added along the way. Okay, and now things get complicated. And I don't really expect you to follow this, but I was listening to a lecture once, and the lecturer said, you know, he didn't expect anyone in the audience to understand this, but he said, listen to the music of it. And I liked that. And I felt like I actually could listen to the music of it. So listen to the music of this. This is our differential equation, right? We're doing gradient flow and we're adding noise. Now, this differential equation, if we assume a density, a probability density on model parameters, okay, so I'm going to assume that at each point in model space, at each point, there's a probability density. Now think of this, this is related to Brownian motion. Think of this as perfume diffusing through a room, right? So if I open a bottle of perfume, the perfume molecules diffuse through the room. And if the molecules were, so they diffuse out, and if the molecules are heavy, they're going to have a tendency to fall down. So they'll concentrate at low energy or low loss. But at the same time, the fact that it's random, that they're diffusing, is going to prevent them from concentrating right at the lowest loss because they're jiggling around and they'll jiggle back up. So there are two flows involved. There's a flow due to the gradient of the density called the diffusion flow. So the perfume will flow from high density to low density. If it's concentrated more at the bottle and concentrated less nearby, there's a flow of the perfume molecules towards places where there are a lot, toward places where there's less. It just diffuses, independent of the energy, independent of gravity, pulling them down. And there's also a gradient flow. Each perfume particle will fall due to the force of gravity, assuming it's a heavy atom, heavy molecule. It'll fall due to the force of gravity. So there's a gradient. There's a gradient due to the gradient is pulling the parameters in a certain direction, right? In this equation, the gradient is pulling parameters in a certain direction, and this term creates a diffusion flow vector. And a stationary distribution is a distribution that doesn't change, right? So what we're going to ask ourselves is, what's the stationary distribution here? And the stationary distribution is when these two flows cancel, when one is the negative of the other. So, the diffusion, which is, the gradient, you're going to have a gradient, say gravity pulls the perfume toward the floor, but then you're going to get a gradient, a gradient in the density, and the diffusion process will push them back up. And when those two flows are equal, we get a stationary distribution. So we can write down the equation that says these two flows are equal, and then we can solve it, right? So this is the equation saying the two flows are equal. I take this density, P is the density of the probability of the density of the perfume molecules, how dense they are, and I can divide by it so that I get a gradient. So that now you get a gradient in phi of the density divided by the density, and this is just the gradient of the log of p. P is just a scalar. So now I have an equation that two gradients are equal, right? The gradient of the energy of the loss is equal to the gradient of the log probability. And if two gradients are equal everywhere, then the two functions must be the same. So it means that this log probability is proportional to the negative loss. Now, if the log probability is proportional to negative loss, the probability is equal to, if I just exponentiate both sides, and z is a constant that gets introduced when you integrate. If I just exponentiate both sides, I get the probability of phi is equal to 1 over z times an exponential in the negative of loss. Okay, so this is getting close to the Gibbs distribution, right? The Gibbs distribution said in physical systems, the Gibbs distribution says that the probability is proportional of a state is proportional to e to the minus entropy over kt, e to the minus energy over kt. So this is saying, so we get this equation. So this, okay, what is this equation saying? It's saying that we've got a stationary distribution in this stochastic differential equation where we've got a gradient plus stochastic noise that has a stationary distribution that's a Gibbs distribution. Okay, now earlier I said the probability of a model given the training data is exponential in the loss, right? We derived that. We defined the loss to be a cross entropy loss with a regularization term. And we showed that the posterior on the model parameters is an exponential in the loss. Now, we've also shown that the Langevin stationary distribution has the same form. So if we simply set the sigma in the stationary distribution to be the right constant, then this SGD plus noise, it's a theorem, assuming this stochastic differential equation formalism, it's a theorem that SGD plus noise under right, as the learning rate goes to 0, but the noise stays constant, samples from, it has a stationary distribution, if it converges to its stationary distribution, it's sampling from the posterior distribution on the model parameters. So I hope the music came through. A general stochastic differential equation. So I said differential equations are the scariest thing in deep learning. Here's the general form of a stochastic differential equation, and I've written it out in terms of delta t's. So it's saying the value at t plus delta t, and I want to think of delta t as being infinitesimally small. Really, you want to think of delta t as being differential, dt. But dt is hard to talk about for reasons I'll explain. So think of this as being a very small delta t. And so x of t plus delta t is x of t plus some linear direction that you're moving. And it's usually written as mu. This is the gradient term. This is the gradient. So some direction you're moving, and that direction can be a function of both x and t times delta t. So this is an ordinary differential equation. If it was just this, without this, you'd just be integrating an ordinary differential equation that says dx dt is equal to this mu term. This is the rate of change of x as a function of x and t. Okay, but then you add this term, and this is a noise term, and what you get as delta t goes is delta t is small enough, this will allow you to directly sample from t plus delta t by doing the linear term plus the noise term, right? It's the same idea that you can jump ahead in your sampling because you're just adding together a bunch of Gaussians, if you were to take it to be a fine enough structure. Okay, now there's something I want to point out about this. It's important, it's really strange. Suppose I took this, this x of t plus delta t, that's going to define a delta x. So delta x is the sum of these two terms. This is how much, this is delta x. This is how much x changes. If I divide delta x by delta t, I get square root, this term becomes just the normal derivative. Delta x over delta t is that value. However, if I take this term and divide by delta t, I get square root of delta t over delta t, and it doesn't cancel. You get 1 over the square root of delta t, which goes to infinity. So the derivative of this is infinite. It's a continuous function at any finite delta t. As delta t goes to 0, delta x goes to 0. But it goes to 0 at the rate of the square root of t, not t, not delta, square root of delta t, not delta t. So it has no derivative. It's not differentiable. It's everywhere continuous and nowhere differentiable. And this is usually written as dx equals this times dt plus this times dB. And this is the differential of the Brownian motion. That's this term. I find this obscure notation. To understand it, I really write it this way and realize that this term is, this dB is much larger, sort of infinitely larger than that dt. That's hard to think about. So if you think about it in terms of a finite step, this term is arbitrarily larger than that term. But this is the general way of writing a stochastic differential equation. And these two expressions mean exactly the same thing. I just find this less clear to me. Okay, now I started this by saying the motivation here was to have a better understanding of SGD, stochastic gradient descent. So let's consider stochastic gradient descent. So we have noise, and now I'm going to focus on the noise due to the fact that we've got a finite sample that we're averaging. Okay, so in Langevin dynamics, I assumed the learning rate was so small that we did not have to worry about the distinction between G hat and G. But now I'm going to consider the noise that's introduced by G hat. I'm not going to add any other noise. I'm just talking about the gradient descent, ordinary gradient descent, where the batch sample introduces noise. This is not the full gradient over all the data. This is just the full gradient just over some mini batch. And if that mini batch is small, this has a lot of noise. And I'm going to consider a step size. I am going to consider a step size such that the model parameters doesn't change much over that step size. So I'm going to assume, so if we, I'm going to rewrite this as G hat equals the true gradient plus the difference, right? So this is just trivial, right? It's just adding and subtracting the true gradient. So we've got a true gradient plus a zero mean. This now has zero mean because the average of this, the average of this is that. The true gradient is just the expectation of the estimate of the gradient. So we've written the gradient as a true gradient plus noise. So I can rewrite this as phi of I plus n is phi of I minus, now this is going to be the standard gradient descent update. If we're doing it in the appropriate way, where we scale the learning rate with the sample, with the mini batch size. So I'm writing this as there's a true gradient, a true linear term plus minus eta times a noise term, right? This is now a noise term, zero mean noise term. Now, if n is large enough, this becomes Gaussian by the central limit theorem. Even in high dimension, if you add together enough random values with the same covariance matrix, you get the sum becomes distributed like a Gaussian. So this is going to act like Gaussian noise. So this term is going to be approximately Gaussian if n is large enough. Think of n as the mini batch size. So I'm going to rewrite this, which I had before. I'm going to say this is approximately Gaussian, so I'm going to rewrite it to actually take a Gaussian sample. And this is going to be approximately correct to the extent that the central limit theorem is approximately correct. So now we're going to take our delta t to be, we're going to take this to be our delta t. And so now we've got an equation that's very much like the equation we had for the Langevin dynamics. We've got phi of t plus delta t is equal to this term, the gradient times delta t, plus this term that goes like the square root of delta t over eta. Okay, so now, and I've just rewritten it. I can rewrite this way. Again, just listen to the music of it. So now I've got an SGD, a model of SGD that turns SGD into a stochastic differential equation. So this is a stochastic differential equation that is a model of stochastic gradient descent, where we've taken a batch size such that the model is not changing much over that batch size, but the sampling is adding noise. The batch itself has noise in the gradient. So here, this is the square root of the covariance matrix. So if we do this in one dimension, let's just consider this equation in one dimension. So now we're adding this square root of a covariance matrix. Well, in one dimension, it's just the standard deviation. So we can do the same analysis that we did with Langevin dynamics and show that we get a probability density on X that goes as 1 over Z times this exponential. So this equation looks just like the Langevin. This equation is just like the Langevin dynamics equation, except that rather than the noise coming from adding noise, the noise is coming from the fact that we're sampling mini batches, and the mini batch gradients are just approximations of the gradients, and that's where the noise is coming from. So we're just replacing the Langevin noise by the mini batch noise. And so the same analysis gives us this exponential form. And this, I promised earlier that we would formally derive an interpretation of the learning rate as temperature. And this in one dimension does that. So this finally, we have basically in terms of this model, for this model of gradient descent, where we're taking the sampling, the mini batches to be the source of noise, we are getting a theorem in this model that the stationary distribution has this form where the learning rate is acting as the temperature. So this gives us a formal interpretation of the learning rate as temperature. Now we can do this in higher dimension, but in higher dimension, the theorem breaks. In one dimension, we get this nice learning rate. In two dimensions, we can give a counterexample. So the counterexample says, consider we have two dimensions, but the loss function is completely separates into a function of the first dimension and a function of the second dimension. If the loss, then the gradients separate. The gradients on the first dimension are separate from the gradients on the second dimension. So the models is going to, those two dimensions are going to behave completely independently. And when the two dimensions behave completely independently, the probability density of a particular two-dimensional vector, x and y, the probability density on, here I'm using x and y as model parameters. The probability density on the two model parameters is just the product of the two, the probability of x of an xy pair is the product of the probability of x and the probability of y, and that can be written this way. Both of them are exponentials, so when I take the product of exponentials, I get an exponential of this form. This is the noise due to sampling mini batches for x. This is the noise in the x gradient. This is the noise in the y gradient. And if the noise in the x gradient is different from the noise in the y gradient, I effectively get different temperatures in the two coordinates. So once I go to higher dimension, I don't have a single temperature. I have a temperature for each eigenvector of the covariance matrix. But however, it is possible, and I'm going to try to quit here and go through this just very quickly, just show you the bottom line, what the result is. It's possible to derive an algorithm that basically normalizes the covariance matrix. So if instead of just taking eta times the gradient estimate, I introduce a matrix that corrects, it's going to try to correct for this fact that we're not getting the same temperature in every coordinate. And we'd like to get the same temperature in every coordinate, because that's, if we have a prior probability that's assuming an isotropic prior on parameters, it would be nice to have, to be getting something that's sampling from the posterior distribution. So what I'm going to try to do here is introduce this matrix D and solve for D in such a way that the stationary distribution has the same temperature, is the Gibbs distribution. It has a single temperature. It does not have a different temperature for each parameter value. And the bottom line, I'll just go to the bottom line. If we take D to be the covariance matrix of the gradients samples, inverse, then it works. Then we get a Gibbs distribution. So this, we can solve for D and get a Gibbs distribution. So what I've done is I've said, if I let this be the inverse of the covariance matrix of the noise, then this form will give me a Gibbs distribution with one temperature, the same temperature in all dimensions. And you can argue that that's a desirable property. And the slides have a bunch of very complicated derivations of the flows I claimed. All right, that's the scariest stuff in deep learning, stochastic differential equations. And we'll review stochastic differential equations when we get to diffusion models. But the bottom line is there's Brownian motion, which is what diffusion models are based on. There's Langevin dynamics that adds noise such that we get a process that samples from the posterior. Or we can model SGD itself in terms of a stochastic differential equation that's going to give us in general different temperatures in different directions as a stationary distribution. But we could correct for that if we could compute the inverse of the covariance matrix and get a Gibbs distribution with the same temperature in all coordinates. So diffusion models, Langevin dynamic sampling, and stochastic differential equation models of SGD that give us Gibbs distribution, stationary distributions. That was a lot. And I'll see you next time.